So, so I guess what I'm trying to say is sometimes it's to your advantage if you can simplify the expression before you actually do the derivative. The derivative is a lot easier to do. And we're going to see that that actually becomes a big issue when we start talking about anti-differentiation, which is what we're going to do today. In fact, I think I want to make sure that I say this now. So chapter 1 last semester was on limits. We talked about what limits were and why they were important. And the first thing that we should have learned last semester was that we need limits for continuity to know that something's continuous. We also need limits for this. Now, we didn't actually use the limit definition for these derivatives, but guess what a derivative is? It is a limit. In fact, you guys might recall that last semester in the past, we would have had something like f prime of x is equal to the limit as h goes to 0 of f of, anybody remember what it is? X plus h, or delta x, minus f of x all over that. Do you guys kind of remember that formula? Yeah. That was the very first lesson of derivatives that we did, and that's when you had to do all that real hard algebra to get the derivative. You remember that? And at that time, you guys were like, man, that sucks, right? But then we quickly learned the shortcuts, right? The rules that made like finding this derivative very simple. In fact, it's super easy. I could teach that to someone in middle school, no problem. So what I'm trying to tell you is today I'm actually going to, instead of showing you the hard way to do integration, today I'm going to kind of give you the short. So we're going to kind of do it reverse. I'm actually going to show you how to find the integral of something the easy way before I show you how to do the hard way. Does that make sense? And you won't be required to do the hard way all the time. Just like here, none of you said, oh, yeah, I'm going to do the limit as h goes to 0, blah, 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 blah. None of you did that, right? You all just said, oh, I'm going to use the power rule. Oh, I know that the derivative of cosine is negative. That's something you memorized, right? Here, oh, the derivative of e to the t, that's e to the t. The derivative of a constant, that's 0. Those are the rules, right? Those are the shortcuts. So that's what we're going to do today. So let's go ahead and get started. So what is an indefinite? Oh, by the way, I should probably, let me pause here for just a second. Let's keep that. And I want to go to the Canvas course. Hopefully you guys have already logged in and looked at my Canvas course. Those of you that had me last semester, oops, not pages, are familiar with it. I want to do modules. Oh, this morning I posted an announcement. Did you guys see that by chance? So I don't post announcements very often, but when I do, you should probably check them out. This announcement is just in case, more so for students that didn't have me last semester. Anything that you need to know can kind of be found, like there's the schedule. How do you join my Google Meet? How do you get to the homework? How do you get to all that kind of stuff, okay? The other thing is, oops, hit the wrong button here. Let's go to modules. This week, this is what our goal is going to be. Today, we are going to focus on section 4.1. Guess what we're going to do tomorrow? We're still going to focus on section 4.1. That's all we're going to worry about this week. Most of this semester, each week we'll cover one section, okay? Now, ideally, there's a video right here, and I realize that most of you probably haven't had a chance to watch this because it's the very first day of school, but I'd like you to watch this video, and it's just me giving you some ideas of how I structure this class. I've already created a video on this lesson that's posted on YouTube. My guess is none of you have watched it yet, right? Because today's the first day you thought about school. Next week, there'll be another lesson, and I will already have it. The video is already created. In fact, it's already there. It's just you can't access it yet, okay? Today's lesson, the things that I'm doing right now, this presentation I'm doing, is in addition to this. Does that make sense? Because I really only get to see you guys that are here once a week, and then tomorrow you guys will be virtual, right? Tomorrow we'll do different stuff. We will not do this same lesson again tomorrow. So I'm going to try to maximize the time that we have together. Homework, though, guess when homework's going to be due? Friday at 9 o'clock, just like last semester, okay? So those of you that didn't have me, look, I'm just telling you right now, every week homework's going to be due Friday at 9 o'clock, 9 p.m. Does that make sense? Okay. Does anyone have any questions about how this is going to proceed? Okay. So again, what I'm telling you is is the stuff that I'm doing right now is different than what was on that video I posted on YouTube. Okay? And I'm actually recording this too, so it'll be on YouTube as well. So let's go and get started. I'm going to introduce some new notation here. You guys probably have not seen that. Oops, let's go back. So thus far, we've talked about limits. That was chapter 1. We've talked about derivatives, and that was chapter 2, and the application of derivatives is chapter 3. Now we're in chapter 4, and what we're basically going to be doing is we're going to be going backwards. Okay? So for example, and this is probably the most important box of the day, is that little box right there, which is really just one word and then a bunch of symbols. And here's what it says. In fact, let's look over here at this part first. This is probably what you guys feel most comfortable with. Notice that this is a capital F and that's a lowercase f. The derivative of capital F equals lowercase f. If that's true, then we would say that this capital F here, we call it the antiderivative of f. We call it the antiderivative of f. So the derivative of this gives you this. So what I'm saying to do here, this symbol here is the integral symbol. And it basically says you're doing the opposite of differentiation. Does that make sense? You're doing the opposite of differentiation. So for example, what is the derivative of x to the third over 3 plus, and by the way, c is a constant, so we could even put a 4 there, let's say. What is the derivative of x to the third over 3 plus 4? Well, you do the power rule, right? And you'd say it'd be 3x squared over 3, right? And what's the derivative of 4? It's 0, right? So then these 3's would cancel. So you'd end up with x squared. So now you're going to have to shift your thinking. Last semester, I would have had you go from here to here. Now we're going to go the other way. And I'm not even really going to tell you why we do that yet. We'll get to that later. So you need to think of, instead of going this way, we're now going to go back this way. And I got a comment here real quick in the chat. Okay, good. All right. So the integral of x squared dx is, oh, I should mention something else here real quick. You know when I put that 4 over the c? Could I put a 5 there? Would that change it at all? What if I put 10 million there? Would that change anything? What if I put -3 there? Would that change? That doesn't change it, because what's the derivative of a number? It's always 0. So this number is arbitrary. That number could literally be any number. It doesn't have to be 4. It could be any. So we use the constant c. And the reason that this is the integral, the indefinite integral of this, is because the derivative of this is x squared. So we're going backwards now. We're going backwards. This is, again, this is probably the most important slide. And now it's not, this isn't fun right now, because right now you're used to going this way, and now I'm going to ask you to go backwards. Okay. All right, so let's look at another example. You guys, what is the derivative of tangent? We saw that in the warm-up. Secant squared, right? So what is the antiderivative of secant squared? It's tangent. Okay, so the integral of secant squared x, you got to just ask yourself, what derivative gives me secant squared? What derivative gives me secant squared? Well, tangent does. Tangent x. And then you guys will need to start adding on this. This is called the instant, or the constant of integration. You're going to tag on a plus c. And the reason that this is true is because the derivative of tangent x plus c is equal to secant squared x. Okay? So again, last semester you would have done this. Oops, I did that the wrong way, didn't I? Let me try that again. Last semester you would have done it this way. I would have said, what's the derivative of tangent x plus a constant? You would have said secant squared. This semester, I'm going to say, what's the integral of secant squared? And now you're going to tell me tangent. Let's just erase everything on that slide. Okay. Now I'm going to pause here for a second. How are we doing? Does that kind of make sense? Okay. All right. And I need to warn you, I'm going to actually go to the next slide here. There's a lot of stuff here. Don't write all this down, okay? What's the derivative of, let's say, x? What's the derivative of x? It's 1, right? The derivative of u is just 1. So the integral of 1 du is u plus c. Now that could have been an x. I could have said this could be the integral of dx, or I'll say it's 1 dx. What is that? Well, it's x plus c. Why is that true? Because what's the derivative of this? Does that make sense? Okay. All of these rules right here, and there are 20 of them, are things you already know. The difference is you guys would have went the other direction. Okay? So in the coming days, we got to start kind of practicing this and going backwards. By the way, if your differentiation rules are weak, it's going to really come back to bite you now. Okay? It's going to come back to bite you now. The most general and by the way, you might be asking yourself, why are these used, Mr. Allen? It's because of U sub and chain rule. Chain rule. Okay? You guys remember chain rule? Remember that first warm-up problem we did? Let me go back to that. Not the first one, this one right here. What rule did you have to use to get that derivative? You would have had to use the chain rule, right? That's why this was a 14 and not 7. And then we'll talk more about u substitution later, but that's why these are in terms of u instead of just x. By the way, the variable doesn't matter, okay? All right, so we adopt the convention that when a formula for the general antiderivative is given, it is only valid in that interval. So for example, consider the function 1 over x squared. You guys would agree that its domain is all x's not equal to 0, right? Because 1 divided by 0 is undefined, correct? So what I'm telling you is this. If I ask you what the derivative or what the integral of 1 over x squared is, we assume that we're only talking about all the numbers that are not equal to 0. So you don't have to say, hey, don't worry, x can't be 0. It's implied, okay? It's implied. I'm going to actually skip this next slide, and I'm going to move on to an example. Okay, so now I'm going to introduce something else. This is something called a differential equation. This is probably the first time you've heard those two words together. Has anyone ever heard of differential equations before? Okay, so you guys know what the word equation means, right? What's an equation? Well, it has to have an equal sign, right? No big deal. Can you guess what differential means? It means it has to have a derivative in it. That's exactly right. Do you notice that this equation has a derivative in it? So what I'm basically, when I ask you to solve a differential equation, which is that's what that is, it has a derivative in it and it has an equal sign. I'm basically asking you, what's the equation without the derivative? What's the equation without the derivative? In essence, what I'm saying is that y is equal to the integral of this 5x to the 4th minus secant squared x. And we're doing that with respect to the x variable. That's why I put dx there and not du. Now, I bet, maybe, my guess is some of you can already solve that. Remember, we're doing differentiation backwards. Did you give it a shot? In fact, we've already talked about that one, haven't we? I got another chat here going. Okay, he's already got an answer. All right, so let me show a little bit more work here. So this is going to be equal to the integral of 5x to the 4th dx. Now I'm kind of getting into something a little bit past We'll talk more about this later on in this chapter when we get into the properties. But essentially, I'm just saying, if you've got a polynomial in here, and actually this is kind of an interesting polynomial because it's got a secant, we're basically saying, what is the antiderivative? What's the antiderivative of 5x to the 4th? X to the 5th. Does that make sense? So this is going to be x to the 5th. Does everyone understand why that's x to the 5th? And if you're not sure, guess what you do to this? Do the derivative, and that's 5x to the 4th. Check. What about this one? Tan x. Now, this was minus, so I'm going to put minus tan x. And can anyone think of what's the last thing I need to make sure I add on here? Plus c. Now, guys, we're going to talk a lot more about that plus c, but here's what you need to know. In fact, let me erase this stuff here at the bottom, and let me make sure I'm doing my time okay here. Because I'm only supposed to teach for the first hour, and then I'm supposed to give you support time. So I want to make sure I honor that. And by the way, guys, I'll probably be shorter than an hour, but I just want to not go over for sure. Okay? So this is my answer. Oops. Anybody want to take a guess on how I could check this answer? How would you check that answer? Just do the derivative of it. So let's check our answer here. So we're just going to do y prime. The derivative of x to the 5th is 5x to the 4, right, by our power rule. What's the derivative of tangent? Secant squared x. And what's the derivative of c? A 0. And in fact, I'll just put plus 0 even though, plus 0, even though we don't really need that on there. It's just 0. In fact, I'm going to erase it in just a second. It's 0, so it doesn't have any impact on this at all. And now all we've got to do is we've got to say, does this look like that? And it does, so we got the right answer. Now, if you kind of followed that example, you're in great shape. Because I did two things here. We just talked about this new thing called a differential equation. You solved it using integration, even though you don't really know what integration is yet, right? I just told you it's the opposite of differentiation, right? Comments or questions on this? Good? Okay. All right, so let's go ahead and move on to the next example. And I don't have a bunch of examples today. I'm going to have you guys do some practice here in a second. In fact, I actually just remembered there's something I might have forgotten to do. Hopefully we can get that figured out. Let's try a harder one. And I'll give you a hint. There might be a word at the top that will help you understand how to do this one. It says rewriting. Do you remember on the warm-up I gave you that 5th problem? And I kind of set you up on purpose. I knew you'd make that harder than it was. Is there any way we can simplify this example? Is there any way we can simplify this example? So let's just look at this cosine theta, and then we have sine theta, and I'm just going to write it in kind of an interesting way. I'm just focusing on this cosine theta over sine squared theta, right? Would you agree that it's the same thing as that? So I know this is a trig thing, and actually this isn't even trig really yet. But does anybody know what that is? It is cotangent. Oops, theta. Sorry, theta. What about that guy? Anybody know what 1 over sine theta is? Not cosine.
Is it cosecant or
cosecant?
I was like, where are the other ones?
Now, would you guys agree that this is equivalent to cosine over sine squared theta? Would you guys agree with that? And I know that some of you, trig isn't your favorite, but hopefully that kind of makes sense. In other words, what I'm saying is that the integral of cosine theta over sine squared theta d theta, our variable here is theta, which it could be x. If you prefer x, change it to x. I don't care. Is equivalent to the integral of, I'm going to write it this way, cosecant theta cotangent. Oops, I don't need an A there. I need a theta. And here in just a second, I'm going to go back and we're going to look at that big list. Now, some of you may already actually be looking at this and know the answer, maybe. But let's not say yet, okay? So I'm saying that this integral is the same thing as this integral here. So now I'm going to go back to this list, back several slides. See this one right here? Now, you guys probably don't remember this, but the derivative of cosecant is actually negative. The answer is to our problem. Negative cosecant theta plus c. That's our answer.
Mr. Allen, you kind of cut out on my computer. Could you explain the derivative again or the backwards derivative or whatever?
Are you asking me, Lucy, to explain this step here?
Yeah.
Yes. Okay. So what I'm going to do is I'm going to go back, Lucy. In fact, let's go back to this example here real quick, Lucy. So at this point, let's focus only on this step right here. This was example 1. I had secant squared dx and I was wanting to integrate that, right? You guys are very familiar with I think you are at least, that the derivative of tangent is secant squared. Would you agree with that? Most students know that one. But I'm going to go back here to this table, and I want us to look at where would that have been? Oh, right here. Okay, and I know the writing here is very small, but this says the integral of secant squared u du is tangent u plus c. In other words, what I'm saying is the derivative of tangent is secant squared. So the question you can think of when you see this integral symbol is the derivative of what gives me secant squared? The derivative of what gives me secant squared? The answer is tangent. Agreed? So in this example number 2, we had, oops, too far. We had this right here. And so the question is, the derivative of what gives me cosecant theta cotangent theta? Well, here's the answer. And the way we could see that is coming back to this table right here. The derivative of negative cosecant squared, or negative cosecant u, is cosecant u cotangent u. Okay, does that help, Lucy? Okay, thank you. Thank you for asking.
Yeah, can you put that table like on Canvas?
I can.
Okay.
I actually have. Yes, I'll write that down. Just to let you guys, I don't know if you guys remember when I put the derivative table on Canvas with all the derivatives? I did that last semester. Yes, no, shake your head if you're on virtual land. Okay, I'm going to post that one again, and I will post this one too, okay? And by the way, guys, I'm just going to let you know right now, this example 2 I did, this is a tough one, right? This is definitely one that if this, so right now in the reality that we live in, most of our assessments are going to be virtual, right? They're going to be on Canvas, which is the way it is, okay, until we get back to some normalcy, which who knows when that's going to be. You guys could just look, you could look this up and find this, right? You could just look at the table. The challenge will be is if on May 4th during the AP exam, we are live and in person, you guys, you would have no reference sheet. You have to memorize these things. In years past, I gave these things called facts quizzes. You may have heard of them if you have any siblings or friends that took me last year. And students hate them at first, but then they appreciate them at the end because it makes them memorize all these rules. Okay. Anyway, so this is kind of a tough example. And the other bad news with this example is if you just look at this, you're going to be like, I have no idea. I have no idea what the antiderivative is of that. So what I had to do is I had to rewrite the problem. In fact, I'm going to do that again on this next example. I'm going to come back to this video in a minute, okay? Let's try another one. I'm going to just shut up on this example. I'd like you to try to think of how could you rewrite that? How could you rewrite that to figure out what the answer is? So give that a shot. There's no trig involved on this one. Okay. Uh-oh. There we go. Would you guys agree that t squared minus 1 over t squared is the same thing as 1 minus t to the negative 2? Right? T squared minus 1 over t squared is equivalent to the t squared over, oops, this is t squared, minus 1 over t squared. So I'm just doing basic algebra here. I'm not doing anything funny. So what I'm saying now is that this integral, the integral of t squared minus 1 over t squared dt is the same thing as the integral of 1 dt minus the integral of t to the negative 2 dt. And my guess is you already know the first integral, don't you? What would that be? The derivative of what gives you 1? X, but not x. In this case, the variable here is t. That's why we use dt here. So this first one is t. The derivative of t is 1 with respect to t, right? Now, guys, I'm using a variety of different letters today on purpose because I'm trying to emphasize that this dt is telling you what variable you're doing the derivative with respect to. So even though some of you like want to say x here, which is true if this was a dx, but since it's dt, we use the letter t. And remember, the letter doesn't matter. We could have done theta, we could have done z, we could have done whatever variable we want. Now I have a little bit of a harder question here. Does anybody know what the derivative, or I'm sorry, what the integral of t to the negative 2 would be? Yeah. T to the negative 1? Okay. So do you think that's the answer right there? Does this look okay? No?
No, because
It has to be plus.
So should I put a plus right here?
Yeah.
Okay, let's check. Now, how do we check our answer? Let's check our answer. Let's do a check now. We're going to check. And the way we're going to check is we're going to do the derivative with respect to t of t plus t to the negative 1 plus c, right? That's what we're trying to do. That's our check. What is the derivative of t? 1. By the way, that's what that is, so that's good. What's the derivative of this? T to the negative 1.
Negative t.
Shoot. Sorry, guys. Negative t to the negative 2, right? And then what's the derivative of C.
0.
Oh, by the way, are we good? We're good. Nice job. This is our answer. So we did need to change that minus to a plus. So again, guys, last semester you would have been given this to do the derivative of. Now we're doing the antiderivative. And one of the hardest things to get through your head about the anti-differentiation piece is a lot of times you want to rewrite, you want to simplify algebraically before you try to do the integral. Okay? You want to simplify it first and then do your integral. Comments or questions on that one? Checking is, the beautiful thing is, it's kind of like, do you guys remember in Algebra 1 when you were doing factoring?
Yeah.
You'd have something, and this is a completely unrelated problem, but let's say I gave you, x squared minus x minus 6, and I said, what's that factored, right? And hopefully you guys remember that'd be x minus 3 and then x plus 2. And that'd be your answer, right? Do you realize that, guess what you could have always done on a quiz or a test? You could have foiled it to check your answer, right? It's the same thing here. Now, obviously, it's a little bit more difficult than algebra, though, right? We're doing a little bit of calculus stuff. Okay, I'm going to go ahead and move on. All right, so I have shown you antiderivatives. I've shown you we're just doing some shortcuts. I'm just going to start this one. I'm not going to finish this one because I want to get to the application. I want to do one application before we call it time here, and we're about 12 minutes away from 45 after. So I want to stop with and honor your time for questions or if you want to work on homework or whatever. So can you guess what I'm going to do first in this problem? I'm not going to finish it. I'm just going to get it started. Can you guess what I'm going to do first? I'm going to rewrite it. Can you guess what I'm going to do? I'm going to distribute, okay? So the first thing I'm going to do before I actually integrate is I'm going to change this x to the 1/3, right? That's the same thing as the cubic root of x, times x minus 4 into x to the, does anybody know what that is multiplied together?
2/3.
Not 2/3.
Oh.
I'll give you a hint. I'll give you another hint. 4/3 minus 4. Okay, anyways, that's how you'll proceed on this one. Maybe I should do this one, but maybe I won't. I'll just leave this one. So I'm telling you that the integral of the cubic root of x times x minus 4 dx, oops, didn't need that last parenthesis there, is the same thing as doing the integral of x to the 4/3 dx minus the integral of 4x to the 1/3 dx. Now, guys, you still have to do work. You still have work to do here. Should I give you the answer just so you can check it? I'll give you the final answer so you can check it on your own. I'm not going to do any of the intermediate steps. Final answer I got here is 3/7x to the 7/3 minus 3x to the 4/3 plus c. And we're basically doing the reverse of the power rule. The reverse of the power rule. That's the answer. Okay, so I've done several examples of rewriting. If you don't have to rewrite, you just look at that table. Or in this case, you have to use the opposite of the power rule, which we've already seen some examples of. Okay. This is the last example I want to talk about today, and it's an actual application. So I haven't really told you a lot about why or what integration actually means in terms of integrating a function, but I do want to show you one application, and it involves vertical motion. And it says a ball is thrown upward with an initial velocity. So the initial velocity is 64 feet per second. And its initial height is 80 feet. Question A says find the position function. Now, I'm going to do this problem completely with calculus. I'm not going to refer to physics, shortcuts, or anything like that. I'm going to just use calculus. We have about 9 minutes left, so this is perfect. Okay? Anybody want to take a stab on what S of 0 is? Remember, S is the letter we use for position. What is the position of the ball? Is it ball? Yes, ball at time t equals 0. Did they tell us? What's the initial height? 80. It's 80. Does that make sense? So I'm telling you that S of 0 is 80. What is the initial velocity? $64. Okay, good. So you guys with me here so far? And then there's one other thing that I do need to mention. Maybe I'll put this in purple. Does anybody know what the gravitational constant is for the Earth in feet per second squared? Anybody in virtual land?
Is it like 32
9.8.
feet per second?
How much?
32 feet per second?
Close. Negative.
Oh, well, whatever. Same thing.
William, that was a good answer. You understand why it's negative though, right? Does anybody know what this comes from? This is S. This is S prime. Does anybody know what I should put for negative 32? This is actually S double prime. So we know that S double prime of t is negative 32. Would you guys agree with that? That is the Earth's gravitational constant. And by the way, that's rounded, right? It's not exactly that, I don't think. But we'll go with negative 32. So anybody want to take a guess on how am I going to go from here to here? See, in the past, I would have been from here, and I would have asked you to go to here, right? So guess what I have to do? I have to do the antiderivative. I have to integrate. So what I'm going to do, and I'll do this in purple. Okay, I'm already in purple. I'm going to integrate negative 32 dt. Anybody want to take a stab on what the antiderivative of negative 32 is? Negative 32 t. Negative 32t, and then don't forget, and I'm going to put C1. Now, so here's an interesting development. We found that the velocity function is this negative 32t plus some constant. Guess what that constant is in this case? What do we know right here? We know that S prime of 0 is 64, right? So we know that S prime of 0 is 64, and we know that that's equal to what? Negative 32, and what do we put in for t? What's the time? 0, correct? So what's C1? What's negative 32 times 0? So what's C1? 64. In other words, and this is the big idea that we got to get to, S prime of t is negative 32t plus 64. So far, we have been able to calculate the velocity function for this motion. We did it using integration, using the antiderivative. Okay, I'm going to go to the next. I'm going to rewrite this on the next slide, okay? Maybe. There we go. Oh, I don't have another slide. Okay, I'm going to have to use this slide anyways. So S prime of t is equal to, I think we said it was negative 32t plus 64. Agreed? That was our position, or our vector, or velocity function, right? Now, guess what we want to find? The position function. How are we going to find the position function? We're going to have to integrate again. So guys, what I'm trying to get across to you is in the past, you would have went from position differentiation to the velocity, and then you would did the derivative again to get the acceleration. Agreed? Now we're going backwards. We're going backwards. So let's do it again. So this is going to be the integral of s prime of t dt. In other words, this is going to be the integral of negative 32t plus 64 dt. Now let's play around with this power rule a little bit, okay? Let's focus only on this part right here. I've got that negative 32, right? T is going to go to what power?
T squared.
T squared. But anybody know what's going to happen to balance that out?
Divide 32 by 2.
You've already got it figured out. Good. And by the way, I didn't tell you that. You guys just told me that. Plus, and guys, I'm sorry, I'm kind of in another slide here. 64t plus, and I'm going to write C2. The good news is we're going to stop there. We're not going to get to C4 because that'd be a little bit too explosive. Thank you, Luca. Appreciate that. Oh, by the way, this is S of t, right? Anybody want to take a guess on what C2 is? Let me give you a hint. Anybody want to take a guess on what C2 is? It's 80. So let me write this. Let me write it right here. S of t is equal to negative. Well, 32 divided by 2 is what? 16, right? So let's make that 16. This is a 1 here, guys. That's an ugly, ugly 1. Let's get rid of that. It's a 1. Negative 16 t squared plus 64t. And then guess what I'm going to put in for C2? Was it 80?
Yeah.
Oh, okay. Sorry. For some reason, I was thinking 60 there for a second. That is the answer for question A. Question A is find the position function for this. So what I'm telling you is this position function will tell me the position of the ball, the height of the ball, anywhere we want to know after t equaling 0, right? By the way, if t equals 0, what's the answer? 80, which is what we wanted, right? We want it to be at 80, right? You mind if we play the game again? Can you guess what the answer is roughly when t is equal to 2? Around 140 something, right? We could figure that out. We could literally plug in 2 here and figure it out. Okay? So now the last question here. When does the ball hit the ground? Well, we can look at we've got the graph here. It looks like it happens at, so how, let's say you didn't know, you didn't have the graph. How would you figure it out? What's the height of the ball when it hits the ground?
0.
So guess what you put right here? Yeah, so let's go ahead and do B now. I'll do it in red. So for B, we're basically saying, question mark, when is S of t equal to 0? So then we would just do that. 0 equals negative 16t squared plus 64t plus 80. And it would be horrendous to do that, wouldn't it? Would probably be the easiest way to do this problem if you didn't know it. Yep. You guys remember this? Anyways, that we could have done that. It should be, yeah, there we go. That'd work. The answer is 5. The answer turns out to be t equals 5. Anyways, I'm going to stop there. So guys, what I'm going to do now is I'm going to stop recording, first of all. Stop recording. What I'm going to do now is I'm going to stop.